The first thing you need to find is the warm-ups page with the coordinates of an angle on the unit circle. I feel like these will go faster today because we're, kind of used to the process now. So we're going to do problems 4, 5, and 6. And in number 4, I'm hoping you notice the denominator is 4. So I'm going to go 0, 4 pi over 4, 8 pi over 4 to start. So first step is to label my 0, 180, and 360. Then I say to myself, self, is this angle 7 pi over 4 going to be in the top of the circle or the bottom? In this case, it's the bottom. And then I say to myself, self, what do I need to split the bottom into? 4s, 4 equal pieces. So I try to do my best to split the quadrants down the middle. Yeah, that one's not great. This is why we have erasable pen. So I try to cut that bottom half of the pizza into 4 equal delicious pieces. And this is 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. Okay, now if I'm in quadrant 4, I find the reference angle by subtracting these two. I don't think I need to show my work. Do you? Everyone in the class can do 8 minus 7 is 1. So I'm just going to write pi over 4 up here as my reference angle. And what degrees is pi over 4? You don't even have to think about it. Think about it this way. If I split a quadrant into 2, which means I split a 90-degree angle into 2, pi over 4 is 45. Okay, why do we need that? We need that so we can pick the correct triangle to use for our labels, and we're going to use the 45, 45, 90. I'm hoping that there's also, if you're drawing this at all to scale, there's kind of a hint about what triangle to use just from the scale of it, that two sides kind of look equalish. Is anyone thinking to themselves, I wonder if the denominator is 4, if it's always 45 degrees? Yep, pretty much, pretty much. Okay, so my labels are 1, square root 2 over 2, square root 2 over 2. And then the last thing I need to do with my picture is say, okay, what's positive and what's negative in quadrant 4? In quadrant 4, this is positive and this is negative, and I didn't really leave enough room. Let me go back and fix that. Okay, so my coordinate is over root 2 over 2 and then down root 2 over 2. Over, down. Okay, does that match the answer for what's on my unit circle already? Yep. Okay. Number 5. Pi over 3. Okay, so 0, 3 pi over 3, 6 pi over 3. I don't really even need to hardly label the 6 pi over 3. I can tell that it's going to be in the top. And I'm going to split the top into 3 equal pieces as best I can without a protractor. So 0, 1 pi over 3 is right here. How do I find the reference angle when it's in quadrant 1? I'll accept 2 answers for that. What do I do to find the reference angle when you're in quadrant 1? Yep, minus from 0, or you just know it's that because you're in quadrant one. Either one of those are okay. And what does pi over 3 equal in degrees? Look up to number 1 on this page if you need to. 60. And does that make sense? Because you took 180 degrees and split it into 3 equal pieces, hopefully. Okay, now what triangle should we use then? Perfect. 30, 60, 90. Here's my dude. Now, I'm not for memorizing. I hope that, you guys don't think that I have any way for you to memorize anything. I do think if you're going to memorize something, it would be the labels on these guys. And that's really just for speed. 1 short leg is 1/2. Long leg is √3/2. Then I say to myself, if I'm in quadrant 1, what are the signs? Yep, positive and positive, so I don't need to worry about it. Over 1/2 up √3/2. This is about the time in the worksheet where people go, I get this. Do we have to keep going? Which is great. Okay, let's check our answer. Pi over 3 is 1/2 √3/2. Perfect. Oh, good. We have a new denominator. That'll help us keep interested in this problem. 6 pi over 6. 12 pi over 6. Okay, 5 pi over 6. Is that going to live in the top or the bottom of the circle? The top. And how do you split the circle into 6 equal pieces? Well, this is what I do. I go to the thirds like I was going to do before, like I did on all the ones that are thirds. So this is like what you see people do when they're working in a pizza restaurant. They like cut things in half and then they cut their halves in half. So then come along and cut all of those pieces in half. And clearly mine are not perfect. And clearly that is okay. Those are not 6. Somebody might be really mad if they get this pizza right here. Now that should be the piece that Mrs. Talbot eats because I don't need to be eating pizza. And the smaller the piece, probably the better for me. But I'll want to eat, say, maybe one of these ones down here. Anyway, okay. So 1, 2, 3, 4, 5 pi over 6. And if you are a student who is really with me, you might say to yourself, well, it's probably a 30, 60, 90, and it's probably just a little bit up from 6 pi over 6, and I probably don't need to draw all this other business. Okay. How do I find the reference angle in quadrant 2? Yep, so 6 pi over 6 minus 5 pi over 6. 6 equals 1 pi over 6. And what do you guys think the degrees are for pi over 6? Let me ask you this. What do you think the degrees are if you take 180 and split it into 6 equal pieces? 30. So that means I still go back to my good old 30, 60, 90, even when it's got a denominator of 6. Okay, the x is negative in quadrant 2, and my coordinate is back √3/2 and up 1/2. And then let me check my answer. 5 pi over 6 is right here. Yep, back √3/2, up 1/2. Okay, I'm just going to leave this up here for a minute, take a breath. If anybody needs to fill anything in, please do. Okay, so I passed out a blue page. We're doing that at the end, not at the beginning. We're starting in our notebook. This is going to be kind of weird. We're going to go notebook, resource page, notebook, blue sheet. Okay, so you guys are setting up your notebook. I want you to notice that we have a lot of this chapter left. We're going to spend the entire rest of the chapter doing one concept. And it's just that important. It's transformations of the sine and cosine wave. So we're going to do parent graph toolkit for those. We're going to talk about all the possible transformations. And sine and cosine waves have a new, it's not a variable, it's a parameter that you have not experienced before in any of your graphs. So we're going to talk about that today. And the main goal of today is to talk about that new parameter that you have never seen before. And that's not true. You've seen it. It's just we haven't really addressed it before. And we're going to talk about the general equation. And then we're going to start doing the parent graph toolkit for sine. And then cosine should be tomorrow on the back. So that's the goal. So everything from here on out to the end of chapter is sine and cosine wave graphing, all of the possible transformations of that. And it's super important if you're going to take AP Calc, you should spend a lot of time on it. So just want to make sure that you're set up for that. So I want to talk about the day that you guys went outside with the water bottles. And we do something like this when you got back. Do you guys remember which one of the graphs was from you walking fast and which one was from you walking slow? Yeah, this one's walking fast because you can cover more ground while you're walking, basically. And then the other one's walking slow because you're covering less ground while you're walking. So we're gonna write, hold on. I'm too far away. I also lost my pen. Oh, here it is. Okay, so this graph was the walking fast style. And we called this horizontal stretch. Do you guys remember working on vertical stretch before? We did vertical stretch with parabolas, cubics. What represents vertical stretch in an equation? The A value, right? So whatever the A value is. Okay, now we're going to start talking about a slinky basically being pulled and horizontal stretch. So this one was walking slow because you're covering less ground. Does anybody know what this would be called? What's the opposite of horizontal stretch? Horizontal compression, yeah. I want you to think about it literally like pulling a slinky and pushing a slinky. why I don't have a Slinky today. Don't you think that that would be a good idea? Okay, so we're gonna pause there. So I said uh, we're gonna do notebook, resource page, notebook, parent graph toolkit. There was the first notebook. Now I need you to find the resource page that says 9-117 at the top. And in this resource page, we're going to discover what happens with horizontal stretch and compression. I need everyone in the room to grab a graphing calculator and make sure that it is in radians mode, please. Okay. Check at the top, make sure that it's a radian. If it doesn't say radians, hit the mode button and scroll to where it says radians and then hit enter to change it to radians. Okay, I want you to notice that at the top of the page up here, it says graphing y equals sine of bx. B is the letter that we're going to use for horizontal stretch and compression. So A is vertical stretch and compression, B is horizontal stretch and compression. Can you tell in the first one that B is 1? Okay, so what I'm saying is, what number would be in front of the x if there's nothing there? 1 times x is x, so it's 1. Okay, so above that problem, we're gonna write b equals 1. And this is kind of the regular style. So this is what you would expect to have for the parent graph, basically. There's no horizontal stretch or compression when b is 1. So the first one we're going to do is the usual style. Okay, however, we need everyone in the class to set up their window to look like this. So hit the window button. Again, first make sure you're in radians. Hit the window button. And we want our x to go from 0 to 2 pi. Do you guys know where the pi button is? It's above the little up arrow caret guy right there. So you have to go second exponent button. And what do we want to go by? I think we want to go by pi over 2. And if you hit enter, it's going to convert it to a gigantical decimal. Let me do it again for you so you can see what I did before I hit enter. So I did 0, 2 pi, pi over 2. And then on the y, we want to go from -1 to 1. And your scale can be 1, it doesn't matter. Does anybody need me to go over that again? I totally can. Yes, okay. So 0, 2 pi, enter, and then pi divided by 2, enter. Okay, now go to y equals and put sine of x. And then when you have that, hit the graph button. And you should get a nice pretty wave. That's the whole point. So we're going to take our window here. This is our graphing calculator window. We're going to break it up into 4 equal pieces, which I totally didn't do, but that's fine. And you're going to go, okay, it goes like this. And mine is wonky, but that's okay. And you're going to say to yourself, I can fit 1 cycle in my window. That's because B is 1. And then you're going to say the period. How long does it take to complete 1 cycle? Your period is 2 pi. That means it takes 2 pi to complete 1 full picture of the wave. And then we're going to pick up our work and go faster as soon as we start. You're going to pick up what I'm laying down here in a couple graphs. Okay, now go to this guy. Go back to y equals and change it to sine of 0.5x. And write b equals 0.5 up here. And then just hit the graph button because we want to use all the same settings. Okay, this is kind of a hard question. How much of the wave can I fit in my calculator screen? Half. Oh, you guys, I wasn't even able to trick you. I was trying to trick you, but I couldn't trick you. Okay, so here's the thing. We need to figure out what the period is. The period is, the wave's only halfway done here. Can you picture that it would have to go all the way to here to complete the wave? Okay, what's the answer there? 4 pi. Great. Okay, I don't want you to write that though. What I want you to write is 2 pi divided by 1/2. Keep change flip. Is 4 pi. I really want you to get into the habit of this 2 pi divided into that many equal pieces. What did we do here? This is 2 pi divided into 1 equal piece is 2 pi. Okay, now let's go down to the next one. Change your graphing calculator window. And then what's going to happen is I'm going to stop talking and I'm going to give you time to fill this in. But I'm going to keep doing it with you so you can look up at mine if you want. So sine 2x, b equals 2. Hit the graph button. Oh, look at that. 2 cycles fit in my graphing calculator screen. 2 cycles fit in my graphing calculator screen. So 4 equal pieces. I just did the, no, like, why is it so challenging to draw? Is it because it's early? Pretty sure. Okay. I just missed the 1 cycle. Two cycles. Okay, so now intuitively, what's the period? How long does it take to complete 1 cycle? Pi. But for my math, I'm going to go 2 pi divided into 2 equal pieces is pi. Okay, so the 3 one is the hardest one to draw. I'm going to stop talking. You guys just keep going. I'm going to do it next to you, and you can watch me struggle. It's going to be great. We're all going to struggle drawing the 3. gonna be fine. Totally awesome. Gonna be wonderful. Not at all a problem at all. Mm-hmm. Mm-hmm. Uh-huh. I see what you're saying there, graphing calculator screen. Okay. Halfway there. Fit 3 cycles in, and the period is 2 pi divided into 3 equal pieces, which is not reducible. That's just it. Why is that so hard to, I don't know. It's like you're trying to fit thirds into fourths, five. It's fine. The next one's easier. Kind of. Okay. On this one, I have to fit a full wave in between each of these tick marks. 1, 2, 3, 4. Don't really know why they're starting to lean at the end, but that's, yeah, it's fine. It's fine. It's totally okay. Kind of dreading the 2 pi over 5, gotta be honest. Okay. Uh-huh. Mm-hmm. Uh-huh. Yep. Okay. So 1, 2.5. Whew. Okay, so do your best. Uh, you can grade yourself a 10 out of 10 for your effort there of drawing those very challenging waves. We need to do some definitions at the bottom. So B is the number of cycles. And when I mean cycle, I mean a full wave in 2 pi radians. So B is the number of times that your wave will repeat from 0 to 2 pi. And to find the period, There's a formula. It's 2 pi divided by b, which we did this whole time. 2 pi divided by whatever b was. And then, do you guys know what literal equations are? Have you ever heard the word literal equations? So, you know how in science you had that little like triangle dealio and it was like mass, force, acceleration, whatever? Okay, so if you take this equation, instead of having it solve for period, you solve for b, it's 2 pi over the period. And we use both of these equations. It just depends on the circumstances. One of them is just solve for period, and one of them is solve for b. Okay, once you guys get this situated, you're done with the resource page. Go back to the notebook. Okay, and 117 is the thing we already did, by the way. So now we need to do 107 and write it out like this, kind of stretched out. We're going to identify each of these parameters. And then we're going to start graphing. So when we're identifying the parameters in this equation, you have some old language, but waves have some special language. So I'm going to say the old language, and then I'm going to say the wave-based language for that. Okay, we're going to start at K. K is usually where all graphs start. What is K for any equation? Yes. What I meant in transformation language is it's a shift up or down. But it is typically the y-intercept also. So usually when we're talking in transformations, this is a shift up or down. It's also a shift up or down in waves, but it has its own name for waves called the midline. Where was the midline in all of the graphs that we did a minute ago? Yeah, at 0. So that would be just nothing. Okay, now let's go here. I feel like this is something you guys remember. What does H do? Left and right, right. H is a shift left and right. And for waves, this is called a phase shift. Don't worry, it's just a phase. Okay, don't worry about sine and cosine for a moment, but I do want to remind you sine starts at the midline and ends at the midline. Cosine starts at the top and ends at the top. Now we're going to go to A. A is vertical stretch or compression. Do you know what type of A values give you a vertical stretch? Greater than 1. And compression are less than 1 but greater than 0, so decimals and fractions basically. Um, those are the ones that you see a lot in those like projectile motion problems where you have like 0.15 because it's really wide. Anyway, okay, and for waves, we call that amplitude, which is actually where the A comes from. And then B is our new one. And the thing is, B doesn't have a fun name. B, if you remember, is the number of cycles in 2 pi. But we know B equals 2 pi divided by the period. Okay. Now grab the blue sheet that I put in the middle of the table. So as I told you guys, we were going notebook, resource page, notebook, blue sheet. We have done 3 of the 4. We're awesome. We're doing it. Look at us go. Now we're going to apply these things to specifically sine. So we're going to work on sine first. That's the one you're most familiar with. We're going to do cosine on the back tomorrow. And for this worksheet, I'm going to use a highlighter. If you're a person who likes to highlight stuff, this would be a great place to use a highlighter. I almost used purple. Kind of crazy talk is that? Okay. Equation name is sine. Did you guys know that sine is actually a 4-letter word that is pronounced with a long I sound? It's not something bad you do out of the Bible. That was supposed to be funny. Okay, the parent equation is y equals sine of x. You also might see y equals sine of theta. The locator point is the same as all the locator points in our whole year, minus, I think exponentials had a different one, hk. And the general equation is y equals a sine b x minus h plus k. If you need to know what any of those parameters are, you can look back in the notes that we just did. You're going to do so many of these that you're not going to need to look at that for very long. In the other info, we're going to put those 2 formulas that we came up with on our resource page. B equals 2 pi divided by the period. And these are really the same formula. It's just one is solved for a different letter. Period equals 2 pi divided into b equal pieces. You're going to use both of those formulas. It's just that it depends on the circumstances. Like if you're solving for what you're solving for, basically. Okay, on this very first one, we're going to literally graph the parent graph. So y equals sine of x. And I want you to write at the top, A equals, B equals, P equals, H equals, K equals. We're going to write that at the top of all of these. Actually, no, it's fine. It's fine for this one. Usually I leave a little bit more space after P because usually you have to do a little bit of math, but we don't on this one. Okay. Now, comparing this to this up here. What is A? What is the number in front if there's nothing there? 1. Okay, now B would be a number in front of the parentheses with the X in it. What is it if nothing's there? What? Period is a formula. So this is where you actually have to do a little bit of math. In this case, it's 2 pi divided by 1. 2 pi divided by 1 is 2 pi. I'm going to show my work on all the other ones, just not the parent graph. Okay, now H is after the X in the parentheses. What is it if nothing's there? 0. And K is outside of the parentheses. What is it if nothing's there? 0. Okay, so this is how we're going to graph sine in this particular way. And sine, let's draw a little picture in our white space up here. I think it'll help you out. Sine looks like that. That's the general shape of sine. And just a little bit of foreshadowing, I'm going to call this positive sine. Okay. When I graph these, I always start with K. K is the midline, and it's 0, so that means it's the x-axis. Does that make sense to you guys? Okay, and then the next step is I identify the amplitude. The amplitude is 1. So what I'll do is I'll take my straight edge. And do you guys see how there's a little label for 1 right here? I will dash a line to show me the top of the wave. And I will dash a line to show me the bottom of the wave. Now, in this case, do you guys see that the amplitude, that the midline is 0? Normally, if the midline was something else, I would have dashed that also. We're going to do that in our fourth one. So the one down here, we'll practice that. Okay, everybody okay so far? So let me tell you what I did. I identified the midline at 0, and then I went up 1 and down 1 from that to show the tops and bottoms of my waves. Are you guys good? Okay. The next thing I do is I identify my locator point, which in this case is 0, 0. Locator point is H comma K. I'll just write it up there, and I put a point at 0, 0, and I circle it. This helps you identify where your start is, because the thing is, it goes on forever in both directions. So it's a really good idea to like nail a spot down where you started. Is everybody okay with that? Okay, next, I figure out how many boxes on my graph paper is 2 pi. Can you guys see that 2 pi is supposed to be right here? There's supposed to be a little baby pi right there. How many boxes is this on my graph paper? 8. And I will put a coordinate there to mark the end of my wave. I just did, and come back up here and circle this one. So I just graphed this coordinate and this coordinate. I just graphed the start of it and the end of it. And now what I need to do, this is what I call sushi time. Do you ever watch somebody make sushi? They take the big roll and they cut it in half, and then they cut the halves in half. Okay, so I have my sushi roll. This I'm going to graph the middle dot next, so cut it in half. And then I cut my first half in half. That's where the wave hits the top. And I cut my second half in half, and that's where the wave hits the bottom. So I basically need to fit this picture in between my start and end. Okay, then I'm going to highlight that first cycle of wave after the locator point. And then what I do is I back up the train to show that it's going the same way in both directions. So down, middle, up, middle. Done. Okay. The next one we're gonna do is y equals sine of x plus pi over 2. We're taking little baby steps here. What value is this in my general equation? What did I put in? I put in an h. I put in an h. Okay, so put a equals, b equals, p equals, leave a little bit of space. We don't have to really do any math on this one again, but we are going to have to soon. Just get in the habit of leaving a little space after P. Okay, I'm going to point right here. In this problem, what is A? 1. What is B? 1. Period is 2 pi divided by B. 2 pi divided by 1 is 2 pi, which we already know is going to be 8 boxes on this graph paper. Okay, here's the big thing. What is H? I need to hear you say negative pi over 2. We've switched the sign just like all the H's for your whole life. And what is K? 0. Okay, midline is 0. Amplitude is 1, so I'm going to go up 1 and down 1. Okay, next step is locator point. What's the locator point for this one? Negative pi over 2, 0. Beautiful. Negative pi over 2, 0. Circled. How many boxes away is the end of the wave? 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8. You could also think of it as a horizontal shift 2 boxes from the previous one you did. If I shifted this back 2, then this would be shifted back 2 also. Okay, now I'm going to say, all right, I got to fit this picture into this spot. So I'm going to break this in half. So 4 boxes in is going to be this dot. And then 2 boxes in is my high. 6 boxes in is my low. Highlight. And voila. Okay, we're just gonna write down the next one and then be done. We will finish this on Thursday morning. Okay, the third one we're gonna do is y equals 2 times sine 1/2 x. So what things did I put in there? A and B, right? And I'm just gonna put this part. Okay, and that's where I'm gonna end it.